Hello viewers, in this video we are going to discuss about the concentration of holes in valence band. In the previous video we have calculated the concentration of electrons in conduction band in intrinsic semiconductor. Same exercise is applicable here, but we will do the same thing for holes. Logic is same. If you want to know the number of holes, you must multiply the density of states of holes with the probability of a hole in the valence band. So what we do is, if dpi or dp is the number of holes present inside the valence band within p to p plus dp, the relation for this dp is just like the probability of hole times the density of states for hole. We want the probability of hole means probability of absence of electron. Absence of electron means 1 minus f of e, because it's mutually exclusive. If f of e describes the presence of electron, 1 minus f of e describes the absence of electron, which is the presence of hole. So this is the probability of presence of hole, and this is describing the density of states of holes. So when you integrate this, the difference between the earlier one and this one is, in earlier case the conduction band was extending from EC to infinity, and here it is actually extending from the bottom, which is the 0 level, till the valence band edge EV, because you can recall this is the valence band. If you call this as EV, so from EV till the lower part you may call it as 0. So from 0 to EV this valence band is extending, so the integration limits are different in this case. Okay, now how to calculate this 1 minus f of e? Just same thing, as we know f of e Fermi function, which is 1 by exponential of e minus ef by kBt plus 1. As we know that the energies E here in this case are in valence band. Definitely valence band will be below this EF, because EF will be somewhere in between this, as we have already seen here, somewhere here this EF lie. So whatever E we are calculating here are inside the valence band. So inside the valence band the E's will be less than EF. Therefore here if you take E minus EF is obviously negative. So this is negative quantity, and we have already proved in the previous video that this kBt, which is 10 power minus 19, and if it is room temperature 300 Kelvin, this product order will be 10 power minus 21. So even if it is electron volt order 10 power minus 19, or even in the worst case it is 10 power minus 20, so this is 10 power minus 20, this is divided by 10 power minus 21. So it is ultimately 10 power 1, because 21 minus 20 is going to give you 10 with a negative sign here. So it is e power minus 10, which is a very small quantity. Just like whatever we did for the electron concentration, here I am replacing the parabola here. Earlier we did here, now the parabola is here. So while calculating the density of states, we chose this point as 0 for this dotted parabola, as our parabola is like this, the solid line. So the 0 of the density of states is calculated with respect to EV, and any energy on this dark line, if you refer as E dash, this E dash is of course measured with respect to the valence band edge. So whatever point you measure here with respect to this edge, it is called as E dash, and with respect to ground, the 0, we are calling it as E. Same point refers to E from this side, and with respect to this EV it is E dash. Therefore you can once again bring a relation here. This is a valence band edge EV with respect to ground. So EV is nothing but E dash plus E, or E dash is nothing but EV minus E. So in place of E dash we will be writing EV minus E. Let's come back to this simplification, as we have already proved that this is the smallest quantity, 1 by 1 plus something which is small. So 1 minus 1 by 1 plus the smaller quantity. So here 1 minus of f of e, which is I mean, if you bring this term, as we know, if you bring this term here, 1 into this minus 1, so e power this term survives in the numerator, and 1 minus 1 gets cancelled. So we are left with in the numerator e power e minus ef by kBt, and in the denominator e power e minus ef by kBt plus 1, which is the expression over here. And this, once again, if you divide this term in the denominator, this term drops and it is becoming 1 plus e power this negative term, that is 1 plus e power minus this term. As we know that e minus ef is the smallest quantity, this e power, of course with the negative sign, this is the smallest quantity. Therefore This term, of course, when you pull the minus sign here, EF minus E by KBT, and hence as we know that EF is greater than E, this term is of the order of electron volt, and this term is of the order of 10 power minus 21. This is 10 power minus 20, 10 power minus 21. Still it is 10 power 10, 10 power 1, which is 10. Now it is positive. So after this exercise, it's becoming positive. Therefore, once again, it's a larger quantity. E power term is larger. So 1 can be safely neglected. And finally, this is 1 by this term here, and it can be safely written as e power minus of EF minus E by KBT. So after this exercise, we finally found e power minus EF minus E by KBT as the answer for the probability of hole. Let us substitute it here. As we have already derived from the previous picture, this value is nothing but EV is equal to E dash plus E, and Z of E dash will be gamma times of this. In the previous video, we have called this gamma. What is gamma? This 1 by 2 pi square into 2m by h cross square power 3 by 2, this constant, we are calling it as gamma. It is coming from the density of states function. So this E dash is what we are using here in conduction in valence band. So if you come here, it is Z of E equal to gamma times of EV minus E power 3 by 2. And when we substitute in the actually it is P, it should be P, it's not N, because we are dealing with holes. So the integration goes from minus infinity to EV. See, with the same logic, earlier we have extended it up to positive infinity. Here we are extending it up to minus infinity. Why? Because when you substitute this minus infinity, the probability function drops to 0, below 0. You can check it here, because this probability is e power plus e. When e power plus e tending to minus infinity, this is 0. So there is no probability. So below 0 value, there is no contribution to the integral. Only for mathematical simplification, we are extending it up to minus infinity, just to look like gamma function. Only we are doing this. Now, if you integrate this, of course, there is a negative sign. I forgot to mention here, it's minus infinity, sorry. So this is minus infinity, 1 minus f of e, and when you substitute it here after this, we will get this pi is equal to e power this into gamma ev minus e power 1 by 20 dE. As usual, in the electron case, we took ev minus, of course, it is e minus ec by kbt. Now it is ev minus e by kbt. So we'll take this divided by kbt as some constant y, change of variable for this integral. And if we differentiate this, you see EV is a constant with respect to this. So EV is gone. It is minus DE, and this comes as y, of course, dy times kBT. So dy times kBT. As this minus sign is pulled this side, it is minus kBT dy. So wherever you get DE here, you can safely replace with minus kBT dy. That is first thing. And similarly here, one can substitute y kBT whole power 1 by 2. Because EV minus E is nothing but y kBT whole power 1 by 2. Gamma is constant. Okay. Now let us apply the upper limit and lower limit. If you substitute the upper limit, that is in place of y, if you substitute this EV, so EV minus E, upper limit E becoming EV, which is 0. So y becomes 0 as the upper limit. And similarly for this E, if you substitute minus infinity, minus becomes plus. So it is going to be y equal to plus infinity here. So lower limit is infinity, upper limit is 0. And if you substitute this here, this is 0 to, this is infinity to 0 with gamma e power something y kBT whole power 1 by 2 minus kBT dy. This we have already mentioned in the previous step. Just we have substituted here, nothing great. In place of dE, we got minus. See, if you pull this minus outside, you can simply flip the integral from 0 to infinity. If you take this minus outside, or if you remove the minus, means the integral infinity to 0 is nothing but minus of integral 0 to infinity. You can just flip the upper limit and lower limit. So with that, this minus sign goes, and the limit can be changed from safely from 0 to infinity, which we will do in the next in a moment. Sorry, there is a mistake here. Let me change this value. It should be infinity here, and it should be 0. I haven't made the correction, sorry. Okay. Now, as we know, this integral has EF minus E. EF is constant, and in place of E you can write, of course, this is minus E, or let me calculate E. What is the E? It is going to be E is equal to EV plus Y kBT. In place of E you can write EV plus Y kBT. So if you write this EV plus Y kBT, as already minus sign is there, so this minus is actually EV minus Y kBT. Okay, and you know this minus and this minus gets cancelled, and if you expand this term it is going to be minus EF plus E. So minus EF plus E is nothing but EV minus Y kBT divided by kBT. We have just divided the kBT separately. Now this remaining integral is same, and of course only kBT portion along with Y, of course no kBT gone. We are left with only this Y in the second part, and the other one is EV by kBT. If you combine this term and this term, it is going to be EV minus EF by kBT. EV minus EF by kBT exponent, which has no integral dependence, so it's a constant pulled outside. And similarly, this kBT power 1 by 2, this kBT power 1 becomes kBT power 3 by 2. It also comes outside. And the integral goes from 0 to infinity, e power minus y and y power 1 by 2, which is nothing but y power. You can now write this term, the numerator, sorry, just a minute. This numerator you can write as, inside the brackets, as 3 by 2 minus 1. So I am changing this 1 as 3 in order to make it look like gamma function. So this is basically gamma n, e power minus y, y power n minus 1 with limit running from 0 to infinity is gamma n. So it is basically gamma 3 by 2. So once again it is gamma 3 by 2, and yes, it's gamma n, sorry, gamma n with n equal to 3 by 2. So gamma 3 by 2 is nothing but half gamma half, which we have seen in the earlier integration part. Please have a look at this. Gamma 3 by 2 is nothing but gamma half plus 1, which is gamma n plus 1, and using the identity gamma n plus 1 is nothing but n gamma n. So this half times gamma n, which is half times half, and already gamma half is known as root pi. So this total term is just root pi by 2. So in place of gamma 3 by 2, one can write happily as a root pi by 2. So here also we get the same expression. So this is going to be root pi by 2, and if we substitute it here, gamma exponential of this kBT power 3 by 2 times this root pi, and rearranging is done in the previous way. As we know, this is h cross square. H cross square is nothing but h by 2 pi whole square. So you can write it as h square, and 2 pi goes to the numerator as a 2 pi whole square, as there is a square root in the denominator in this 3 by 2 term. So you can write this as h square, of course 2 pi whole square, square, and this gets cancelled. It is just 2 pi cube. So 2 pi whole cube, which is 8 pi cube. So you can write it as 8 pi cube. 1 pi survives in the numerator, pi square is gone. So it is pi and 8 is there. So this is 2 and this is 2. So 4. So 8 in the numerator and this is 4, which is nothing but just 2 in the numerator. So 2 into 2m h star. See, we are using h star to indicate that this is whole. Earlier we have used E star for electrons effective mass. Now this becomes just h square, as this kBT is also having pi power 3 by 2, and we have a root pi along with another pi which is left over in this h square, h by 2 pi. So that pi and this root pi is nothing but pi root pi, which is pi power 3 by 2. So that pi also goes inside. So ultimately 2 into 2 pi m h star kBT by h square whole power 3 by 2 with the rest over term. It is now EV minus EF, whereas in the other case it will be EF minus EC. That is opposite. That is the only difference. You can recall here, sorry. So for the conduction band case, excuse me, for the conduction band case, yes, this is the term. It is actually EF minus EC if you pull this minus sign inside. Okay. So finally, after doing this exercise, what we found is the number of holes inside the valence band. Now if you call this constant as Nv, earlier we have called that constant as Nc, now we are calling this constant as Nv. The basic difference between Nv and Nc is only this Mh star and Me star, only the effective mass of electron. Remaining constants are same for both, right? So for simplicity, we write this Pi, that is the intrinsic hole concentration. The number of holes inside a valence band of an intrinsic semiconductor is Nv times of exponential of EV minus EF by kBt. So we have derived the electron concentration in earlier video, and we have derived the hole concentration in this video.